This is ELC111, Introduction to Electricity, and this presentation is on semiconductor electronics. Now, semiconductors are group 4 elements, and they include carbon, silicon, germanium, and tin. All these elements have in common the fact that they have 4 valence orbit electrons. This means there's 4 electrons in the outer orbit or outer shell. Now, of the group 4 elements listed, silicon is the most widely used to construct semiconductor devices such as diodes and transistors and integrated circuits. And figure 1 provides us the Bohr model of a silicon atom. And note in figure 1 that there are 4 electrons in the outermost orbit. This is the valence orbit. Now, silicon atoms or semiconductor atoms bond together through what is called covalent bonding. And this means that in the outer orbit, these neighboring atoms share valence electrons. Figure 2 provides us with the two-dimensional Bohr model of the covalent bonding of silicon atoms. Now understand that this structure is really a three-dimensional crystalline lattice structure. For those of you that have taken chemistry, a silicon atom is a tetrahedral shaped atom. But again, it's virtually impossible to illustrate this drawing a three-dimensional view of the atomic structure. The key point here is that when these atoms join together or link together, then they all have 8 electrons in the outer orbit or the valence orbit. For example, if we look at this particular atom here, note that we share electrons with the neighboring atoms. So this particular silicon atom here has 8 electrons in its outer orbit, as do all of the atoms in this structure. And what this does is it really creates a fairly stable material, because atoms are again stable if they have 8 electrons in the outer orbit. And even though these are called semiconductor atoms or a semiconductor material, that name somewhat implies that they're semi-good conductors. However, pure silicon at room temperature is actually a fairly good insulator. However, if we were to add some energy to this, and what I'm going to do is I'm going to add some thermal energy by placing a candle underneath. Let's put a little holder here for the candle so we won't get wax on our fingers. So if I add some thermal energy to this chunk of silicon, then what's going to happen is, of course, when we add energy to any material, that energy has to be transferred, and the energy is transferred by knocking an electron loose from its orbit. So this particular electron here might get knocked loose, and of course it would move up here into this atom. And of course now this atom has too many electrons, so we're going to knock an electron loose from this atom, and that electron might move up here. And of course when it does, this particular atom has too many electrons, so it's going to lose an electron. This electron might go over here. So if we increase the temperature of this chunk of silicon, if we add some energy to it, we're going to see electrons moving through the material. And this is why we have to be so aware of the operating temperature of our equipment that contains electronic components, again, such as transistors or integrated circuits. Now, again, when we have just a chunk of pure silicon, as we saw in figure 2, this is what we refer to as an intrinsic semiconductor material. In other words, it's just simply pure silicon in a crystalline structure. But what we do is we add other elements to this silicon to create what's called an extrinsic semiconductor material. And the elements we add are called dopants. And by adding dopants to the silicon, we can change the electrical property of the semiconductor material. Now, these dopants come in two flavors. They are either trivalent atoms, which have 3 valence electrons, and the elements most commonly used are phosphorus, arsenic, and antimony. And these dopants are also come in the flavor of pentavalent atoms. And these atoms all have 5 valence electrons. And the most commonly used pentavalent dopants, are boron, gallium, and aluminum. So when we add trivalent atoms to silicon, we end up with a missing electron in the covalent bond. For example, we have added a boron atom to this silicon material. Boron, again, having 3 valence electrons, we end up with a spot right here where there is an electron missing from the covalent bond. Now, they call this p-type material, P for positive, but understand that this structure does not have a net positive charge because the boron atom has the same number of electrons as it does protons, so there is not a positive charge associated with having this boron atom in the atomic structure. There's simply a place right here, again, where there should be, everybody would be just tickled to death if there was an electron there to complete the 8 electrons in the outer orbit. But again, we just don't have enough to go around. And when we talk about this structure with p-type material, this place right here is going to be referred to as a hole. Again, it's not a hole in the sense of being a hole. It's simply a place where there should be an electron in this covalent bonding. Now, if we add pentavalent atoms to the silicon, we end up with an unpaired or extra electron in the covalent bond. So in this example, I've added a phosphorus atom to this chunk of silicon. And again, phosphorus being a pentavalent atom, notice that there's an electron right here that is unpaired, or we say an extra electron in the covalent bond. And we refer to this as N-type material, N for negative. Now again, this structure, it does not have a negative charge because the phosphorus atom has the same number of protons as it does electrons. So there's really not an extra electron. They just had to call it something, and they thought N was a good word. Now, this unpaired electron right here is what we will refer to as a free. Oh, I'm having a hard time writing with the mouse. A free electron. And again, it's not really an extra electron. It's just simply an unpaired unpaired electron, or an electron that's not in a covalent bond. Now, the exciting thing happens when we put a P region and an N region together and form what we call a PN junction. Now, understand that we don't just take some P material and some N material and stick them together with crazy glue or super glue. That what happens is that we bombard heated silicon with a gas, and the gas contains either pentavalent or trivalent atoms, and those pentavalent and trivalent atoms diffuse throughout the material. So we have this region of P-type material, and again, remember the P-type material has holes. The holes are represented with the circles, and the N-type material has unpaired electrons or free electrons, and those are represented with the dots. Now, when we put these materials together, form a PN junction, what happens is that we end up having free electrons migrate through the PN junction to fill these holes up. And so we've illustrated that here, that the free electrons are migrating through that PN junction to fill these holes. Now, as these free electrons flow through the PN junction and fill the holes up, we end up with a region in the center here that is depleted of free electrons and holes, because the free electrons again have migrated through that junction to fill the holes up. So we've got this region called the depletion region that is depleted of free electrons and holes. Now what happens is that, of course, when this particular atom right here loses a free electron, it now has fewer electrons than it does protons, and we're left with a positive ion. And this atom on the left side, it has gained an electron, so it has more electrons than protons, and it becomes a negative ion. So existing on both sides of the depletion region are positive ions over here and negative ions over here. And this creates what we call a barrier potential. And for silicon, that barrier potential is approximately 0.7 volts, and that barrier potential is simply due to the electron volt level associated with an electron leaving the valence orbit of a silicon atom. So we've looked at silicon atoms, and those are the group 4 atoms. They all have 4 electrons in the outer orbit. The one that's most commonly used is silicon. And these semiconductor atoms join together through covalent bonding, meaning they share electrons in the valence shell with neighboring atoms. And each atom then ends up with 8 electrons in the outer orbit. And what we do is add other elements to the silicon to change its electrical properties. And those elements that we add are called dopants, and they are either trivalent atoms that have 3 valence electrons, pentavalent atoms that have 5 valence electrons. And by adding those dopants to the silicon, we make P-type and N-type material. And as we see here, when we join these P and N regions together, we have a migration of electrons through the PN junction. And that migration of electrons through the PN junction creates a layer or region of ions on both sides of the depletion region. And this is what we call the barrier potential of the depletion region, or the barrier potential. And that barrier potential for silicon is approximately 0.7 volts.